Okay, hi everybody. We are going to do the new lesson for today. And this is, I'm going to introduce you to here the chain rule in three space. And really, the chain rule in three and four and five, whatever space, is actually incredibly easy mathematically. It's like everything else. I feel like I say this phrase over and over again. When it comes to multi, it's the math is actually not that difficult. It's sometimes the applications and the thinking about it. Okay. But one of the important ideas that I want to revisit here is just from two space. And again, I don't think you necessarily have to write this part down. But there's nothing new here, right? This is if you had a composite function back in the day, and you're asked to find the derivative, right? F prime of x is going to equal f prime of g of x times g of x. Okay. Now, I know when you first learned the chain rule, let's just look at the red here. What you did before, before the chain rule became just automatic is you would do it the long way, and you'd say, well, let's let the inner, right? You said let the inner, let's call that u. And then that would rewrite your function f of g as f of u, right? So y equals f, and f is a function of u. So what this means here is that when you did this substitution back in the day, you said, okay, well, y equals f of u, okay? And then u is equal to a function of x. And then what we would do here is you would take these derivatives. You said that, well, that means this derivative is dy du. This derivative is du by dx. And the way that I get to my desired derivative, which is dy dx, is you simply multiply them, right? And what we really don't spend a ton of time belaboring in Calc 2 space is just, the significance of differentials and the way that they can really be used to talk about not only rates of change, but they're so helpful when we talk about how the differentials cancel, right? Because the differentials of u here, it's a unit that's canceling. After all, it's the unit of u, if you will. Okay. And then, but at that point, I could actually talk a whole lot more about, but that would bring me onto a tangent. Okay. But one thing that I want to mention to you is that this whole relationship right here that we talked about last year is something that we did just in terms of re-expressing a function in terms of another variable. Like that's what we're kind of doing explicitly. And something that we never do last year because it really wasn't necessary, because we didn't really need this visual, is you could also talk about it this way. You could say that, y is a function of u. It's called the tree diagram, right? Like, so y is a function of u, and then u is a function of x. And then what we're essentially doing in this kind of branch or tree diagram is the branches kind of give you directionally, right? So from top down is the dependence to independence, right? So the topmost variable y depends on u depends on x. And then the branches can give you a sense of how the variables are related differentially. So if I look at this relationship right here, if y is a function of u, well, then sometimes we'll put on this branch here, we'll say on this branch that y is a function of u, therefore this derivative is dy by du. And if u is a function of x, then we say this branch here, differentially related, is du by dx. And what we've just done here, right, this kind of branch diagram really illustrates all of this in a really kind of succinct, one could argue cleaner way. And then if the question here is being asked, which is how do I get to dy dx? How do I make my path, right? How do I start with my tree diagram, and how do I get from y to x, which is really what this differential expression is saying? How do I get to a differential relationship between y and x by way of these branches? And well, if you look at the tree, you start at y, I want to get to x, I have to travel the entirety of this path. and the entirety of that path will make me need to traverse the differential relationships of dy du and du dx, okay? Now, in two space, I would argue that this is probably, like, you're probably wondering, why on earth would I ever want this perspective? And really, frankly, in two space, when it's just a matter of a single branched tree, as is this is a single branched tree. It's one vertical path, right? If there's one vertical path, no really need to have this branch diagram. But let's see what happens when you have a multivariable relationship. Let's say I've got a situation like this, okay? Let's say that z is a function of x and y, but then I have that x is a function of a and b, and y is a function of a and b, okay? So let's say we're given a situation like this. And again, you'll notice here I'm not using any particular numbers or variables or functions yet, really, other than just notationally, because once you get the idea, it's actually quite easy to proceed. Well, let's do a tree here. Let's do a tree diagram that again, shows us the dependence-independence relationship vertically. And then let's also fill in the branches, so to speak, with the differential relationship. So here we've got z, okay? Z is at the top. Z depends on both x and depends on y. So we have that vertical relationship again. But then we have x depends on both a and b, and y depends on both a and b. And now what I want you to do, everyone, is I want you to fill in the branches with the appropriate differential relationship. Well, let's see. This branch right here from z to x, the differential relationship here is going to be dz by dx, okay? And the differential relationship here is dz by dy. Note the use of curly d's because these are partial functions, right? Partial differential functions, or I should say z is partially a function of x and y. Well, and then from x to a, this relationship here is going to be dx by dA, right? And here I have dx by dB, and you see where I'm going. Here I have dy by dA. This is dy by dB, okay? So all I've done here is I have mapped out in this new vantage point, in this new way, the relationship between all these variables. Now let's pose the question. If you would please give me an expression for, let's say at the end of the day, I want an expression for dz by dB. What does dz by dB equal? Well, let's see. And here's where it's going to be really important to kind of map out the way we get from z to b. Well, one path is right here, okay? But another path is right here. So if I'm looking at the end of the day, what is the total differential relationship dz by dB, I have to first map out, let's just call this path blue so I don't get confused, okay? The blue path is dz, is dz by dx times dx by dB plus, okay, and then here's the yellow path, dz by dy times dy by dB. And so here's kind of where someone always says, okay, so in general, Miss Yam, in general, when you are asked to find a derivative with respect to some independent variable, true or false, you kind of locate where that independent variable is and you map out the paths. And true or false, Miss Yam, you basically add up each path. The answer is yes, that is true. The reason why you add up the paths, everyone, is the same reason why, do you remember, total differential notation? Total differential notation is talking about how does z change with respect to b in the x direction, added to how z changes with respect to b in the y direction, okay? That's the relationship. That's why you add. All right. So once you have this idea, it's actually quite easy to do the basic stuff. Let's go down here and let's just do a practical practice questions. And what I did here was I just copied a couple pages from your book. So you don't have to write these questions down because they are in your textbook. But let's just go ahead and do a few, and then we'll do a few word problems. Okay. So number 16. Let's do 16 together. So 16 is saying, okay, at the end of the day, they're asking you to find dz by dt, okay, given these relationships here. Well, okay, if I want to get to dz by dt, and see, here's the thing too, look at this, dz by dt, they didn't use the curly notation. Why is that? Well, I'll tell you why. Because look here, the tree is z is a function of x and y, right? But x is a function of t and y is a function of t. At the end of the day, if you look at the paths from dz by dt, at the end of the day, dz is entirely a function of t. It is a function of t fully, if you will. It's not a partial function of t. Okay, so now I'm going to take care of finding the total differential. Okay, so dz by dt is going to equal dz by dx times dx by dt. Notice my switch to regular d's, plus dz by dy times dy by dt. And I just caught my little use of, this should be a straight up, not curlies over here. Okay, curlies should be dz by dt. Okay, and this is going to equal, so I can squeeze it in, dz by dx. It's going to be 3x squared y squared, 3x squared y squared. dx dt is 3t squared, plus dz by dy is 2x cubed y times 2t. Okay, and there we go. I've just found dz by dt. All right. Okay, here's what I want to do. Let's look at number 18. Okay, let's do 18 together. This is more of a word problem, conceptual question. Go ahead and let me give you some time to read it. I think I want to read it with you. A bison is charging across the plain one morning. Okay, his path takes him to location xy at time t. Very good, where x and y are functions of t. And north is in the direction of increasing y. You all ready? All right, and that's okay, that makes sense. The temperature is always colder farther north. Okay, as time passes, the sun rises in the sky, sending out more heat, but also a cold front blows from the east. At time t, the air temperature H near the bison is given by this. Okay. Wow. All right. So, cold front blows in from the east, always colder north. And let's see, as time passes, sun rises. Well, so before I get to all these things here, first of all, H is the air temperature